Okay, so now we are ready to talk about the multivariate Gaussian distribution. Variate normal distribution. Okay, the general multivariate normal distribution, so which means if we had d vectors, we do not require so sigma 1 square does not necessarily to be equal to the second feature variance does not equal to the features of these features, variance of these features, and we denote a random vector follows a general d-dimensional multivariate normal distribution with the location mu and the variance sigma. Okay, so this is a d by 1 vector. This is a d by d. We call it a covariance matrix. Okay, actually, if X follows a multivariate normal distribution, if the PDF of X is given by the X equals to the exponential, actually it is the quadratic forms X minus mu transpose sigma inverse X minus mu. Okay, we have these quadratic forms, and we take a half and apply to the exponential distribution, and we want to make it to be a normal probability, so we need to make sure the normalization constant, so 2 pi to power d, and this is not the absolute value. Okay, this is a determinant. Of the matrix, and here we call it sigma is a covariance matrix, and the sigma inverse is a precision matrix. Okay, let's see what this gives us. Actually, this is given by this one. Let me. Actually, this density function, we can understand it as a composition of the q function, qx, which equals to x minus mu transpose a matrix times a matrix x minus mu. Okay, so this function we already see, right? So if you have the variable x, we know the quadratic form is just this format, right? So we know what this function is. And the next function is just some monotone function, x, which is equals to some constant k multiplied the exponential x, exponential negative half of the x. right? So in other words, if we have the quadratic form of the, and then we give some monotone transformation. So this is the original plot with a contour plot like this. So the minimum point is in the center, and then we apply this monotone transformation. We take the negative. You take a negative, then you have the minimum. You become the maximum, right? So because you have the valley in the center, here you have the peak, and then you multiply a constant, and then you apply the exponential distribution, you get the density. Okay, so this decomposition NQX is just our normal density, very normal density. So this is where the normal distribution is derived. So this gives us a way to simulate the normal distribution. Okay, so I'm gonna use the last plot of today's lecture. Okay, so the idea is, once you have the Bavaria independent normal distribution, so suppose you have two features. This is this is Z1, this is Z2. Suppose we have the standardized normal distribution. Okay, and then we just do the transformation of this Z1, Z2. Okay, we give the transformation sigma square root 2. We get it x1, x2. Okay, so x1, x2 will follow the general normal distribution. So this implies x1, x2 will follow Bavaria normal distribution with mean 0, and variance is sigma, covariance matrix sigma. If you wanted to have some average, you just shift this, you get a general normal distribution. So for today's lecture, if you don't understand the quadratic forms, that's fine. But the basic idea is, the punchline is, you need to, we just give you one way to derive the multivariate normal distribution. Okay, and also for any suppose we have the any x1 xd follows normal distribution mu1 with d locations and the covariance matrix sigma, we can show that the variances of each vector xi is just the diagonal elements in this matrix. So we can write down this sigma equals to the sigma 1 square, sigma 2 square, sigma d square. Okay, and the rest element is just for example, the first one will be the covariance of the x1, x2. Okay, and the covariance of the x1 to xd. Okay, so the variance of each random variable will be the diagonal elements of this matrix. So this will be sigma I square in the diagonal elements. And we can show the covariance of the xi, xj is just equal to sigma ij. Okay, and if we have the diagonal elements, the off diagonal elements are 0, we have the independent normal distribution. And in the next lecture, we're gonna use this general normal distribution to reconstruct our Gaussian discriminant analysis. I think that's all I want to cover today. Thank you.